All right. Has anyone ever heard the name MRI? What does MRI stand for? So, can anyone tell me what MRI is? What is MRI? If you want to tell a layman what MRI is, what would you tell him?
So you excite.
Don't tell me the mechanism. What is MRI? Is it some technique, or what are the advantages or applications of MRI? Anyone? आपने ये नाम सुना पहले MRI? क्या होता है? कुछ पता है? कहाँ इस्तेमाल होता है MRI? Medical diagnostics में इस्तेमाल. So it's a technique. सुनिए बात. It's a technique that is used to investigate soft tissue. Soft tissue involves adipose tissue. Soft tissue could be blood flowing inside the cardiovascular system. It could be the cerebrospinal fluid inside the brain or the spinal cord. It could be ligaments. It could be tendons. It could be muscle, cartilage, skin, retina, the vitreous aqueous humor. All of these are examples of soft tissue. Bone is a hard tissue. For bones, you generally use X-rays because X-rays are attenuated by hard tissue. Whereas it's not possible to look at soft tissue. It's difficult to look at soft tissue using MRI, using X-rays. But MRI is a diagnostic radiological tool. ठीक है? एक radiology का एक tool है, एक diagnostic technique है जिससे हम soft tissue को देख सकते हैं. And MRI is based on a principle. तवज्जो दें. MRI is based on a principle that is called NMR. And NMR stands for nuclear magnetic resonance. And NMR is used by chemists and material scientists all the time to look at molecules, to look at the structure of molecules. It's the most important molecular characterization technique. यार तवज्जो दें. आज बातें क्यों ज़्यादा हो रही हैं? अब देखो बात सुनो. एक ड्रग कंपनी है जो एक ड्रग बनाती है, ठीक है? अब उस ड्रग का एक मॉलिक्यूलर स्ट्रक्चर है. उस मॉलिक्यूलर स्ट्रक्चर को कैसे डिटरमिन किया जाएगा? अगर तो वो ड्रग क्रिस्टलाइज हो जाए, if the drug crystallizes, you can do an X-ray diffraction to look at the internal structure of the drug. One of the most important techniques is NMR. You put that drug, make a solution of it and put it inside an NMR machine. And the NMR machine will give you a fingerprint of the molecule, which is called an NMR spectrum. So the NMR spectrum is basically a frequency axis, and there's another axis which gives you the intensity of some signal, and you get a large number of peaks at particular frequencies, and these peaks of different heights, different line widths. So this is an example of an NMR spectrum. But since NMR has the word nuclear in it, when the technique of NMR went to hospitals and clinics, the word nuclear scares off a lot of patients. Therefore, they did not like to call this NMR. They would like to skip the word nuclear and call this technique magnetic resonance imaging. But basically, magnetic resonance imaging is based upon NMR. Another related technique is ESR. And ESR stands for electron spin resonance. Electron spin resonance is another technique to look at molecules, to look at solids, to find out the structure of molecules. NMR by far is the most important. No chemistry laboratory in the world or university in the world, or a research organization, or drugs company, or any company or organization that looks at discovering new molecules and characterizing them cannot function without an NMR spectrometer. So SSE is also incomplete because we don't have an NMR spectrometer. We're trying to build one in the physics lab. Anyways, these are all related techniques which has something in common. Another idea that I would like to mention is magnetism. Magnetism was discovered about 5,000 years ago by some shepherd who was with his herd of cattle, and he had a stick, and the stick had an iron ending, and the iron part of the stick stuck to a particular rock made of lodestone, which is iron oxide. So magnetism is a very old phenomenon. Chinese used magnetism in the form of compasses to navigate through the planet. Christopher Columbus used a magnetic compass. Arab seafarers used compasses. So magnets are very old. But the understanding of magnetism relies upon quantum mechanics. It was only in the 1920s and 30s that the origin of magnetism started to emerge. So all of these techniques and this phenomenon, MRI, NMR, ESR, magnetism, how hard disks work. Hard disks are the workhorse of magnetic storage. We cannot think of our daily lives without hard disks. There was a time we could not think of our lives without magnetic storage, without audio cassettes which had a magnetic film. So all of these phenomenon techniques, they rely upon one property of the electron or the nucleus, and that property is called the spin. And it's a direct consequence of quantum mechanics or modern physics that the idea of spin emerges. And I gave a motivation, I presented an experiment the other day, the Stern-Gerlach experiment, that gave us the clue that there is such a thing as spin. But the story that I started was incomplete. Therefore, today I would like to complete the picture of the spin, and we will continue this discussion next week. So, what I mentioned the other day, I gave a classical argument. So now what is spin? I would like to elaborate a little bit on the concept of spin. It's a very important concept. It leads to a wide variety of applications. One application, I've mentioned several of these. One application is the emerging field of spintronics. We are all familiar with the word electronics. And some of us are familiar with the word photonics. So most of you want to become electronic engineers. But probably a day will come when most of you would like to become spintronic engineers. Now the field of electronics uses a property of the electron that is called charge. How does a transistor work? You have a gate and a certain voltage appears on the gate and the transistor is switched on and off. So in digital logic you have sequences of ones and zeros. So this is a 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1. So this is how modern digital logic works, how modern transistors work, how the computer industry works. 1 means charge exists on a gate, for example. 0 means charge does not exist on the gate. So these are two binary states. But the electron has another property which is called the spin. What if our electronics becomes free, our circuits become free of charge, rather they use the spin degree of freedom, rather they use the spin property of the electron? That gave birth to a new field called spintronics. So spintronics is an emerging area that exclusively uses the spin property of the electron, and it is robust to noise. It is not as fragile as electronics. There's no RF interference in spintronics. It has other problems, of course, but it has a large number of advantages. It's much faster than electronics. Photonics, of course, is dealing with photons. So these are the three areas that go hands in hand. Every electrical engineer should know about these three interrelated areas. But spintronics is based upon spin. So what really is spin? Hard disks are based upon a device which is called GMR, for which in 2007 Nobel Prizes were given. So GMR, or giant magnetoresistance, can only be described if we understand spin. So spin is a very wholesome concept, and it's an emerging area. The whole area of quantum computing. There are different ways in which quantum computers can be built. One of the most important ways is using the spin property of an electron or a proton or any other ion. So all of these concepts will be brought home by understanding the concept of spin. So in the previous lecture, I presented the idea of that if you have an angular momentum L for an electron, then associated with this angular momentum there is a magnetic moment mu. Both of them are vectors, and you have minus E to M as a constant of proportionality. Okay? If L is quantized, mu should be quantized. The magnetic moment is quantized. And we also learned that if the Z component is quantized, then mu Z should be quantized. Minus E over 2m. M is the mass of the electron, and this turns out to be, if you are inside a hydrogen atom, then Lz is quantized according to ml h bar. So this turns out to be minus E h bar over 2m ml. ये बिन बिनाहट की आवाज आ रही है. ठीक है, अब ये जो क्वांटिटी है इसको बोहर मैग्नेटॉन कह देते हैं, माइनस म्यू बी एम एल. So the magnetic moment is quantized, and whenever you have an orbital angular momentum, that is the electron is in a p orbital or a d orbital or an s orbital. S orbital में तो ये zero होगा ना. बाकी तमाम orbitals में whenever there is an angular momentum, you can associate a magnetic moment with it, and that magnetic moment is generally denoted by a spin. ठीक है, तो Z component भी quantized है magnetic moment का. जिस तरह angular momentum का Z component quantized है, magnetic moment का Z component भी quantized है. So this relationship relates the orbital angular momentum with the magnetic moment. But Stern-Gerlach's experiment showed that if you perform the experiment with s electrons, s electrons के साथ experiment perform करें, यानी silver atoms के साथ, in which the valence electrons are in the 5s state, hydrogen के साथ, where the electrons are in the 1s state, even then you see two distinct patterns. So if you look at the screen, you would observe two spots. You would observe two fringes. The beam will split up. So the single beam that is passing through an inhomogeneous magnetic field will split up. But Bohr's model, according to Bohr's model, the angular momentum is plus minus h bar in the ground state. So if this is the angular momentum, in the Bohr's model there is no concept of the quantization of the Z component. So according to the Bohr's model, if you look at the screen, you should not observe this splitting up into two distinct regions. Rather, you would see one blob that is expanded a little bit, because the Z component lies between these values. देखो, classically Lz is equal to or less than L. Is this relationship valid? You have a vector and you take the z component. Classically, this is what you should observe. So this z component is spread out, but it is not quantized according to the Bohr's model. So if Stern-Gerlach decided to, if the Stern-Gerlach stuck to the Bohr's model, they could not explain the appearance of these two distinct lobes. That is, the fragmentation of the beam into two distinct beams. That was not possible using the Bohr's model. So what others postulated, Stern-Gerlach could not reach this conclusion, but what others postulated is that even if an electron has L0, which means that the magnetic moment is 0 in accordance with L being 0, there is another property of the electron which is called the spin. Capital S, which is equal to S into S plus 1 under root h bar, which is equal to under root 3 2 h bar. That is, small s is half. That is, even if the orbital angular momentum of an electron is 0, that is, even if small l is 0, there is another quantum number which does not come out of the Schrödinger equation, because the Schrödinger equation gives you 3 quantum numbers. It's a 3-dimensional system. There is a 4th quantum number that is beyond the ambit of Schrödinger's equation. Schrödinger की दस्तरस से बाहर है, उसकी ज़हन की हदूद से बहुत आगे है. एक चौथा क्वांटम नंबर है जिसे स्मॉल s कह दिया गया. It's called the spin quantum number. Which always has the value 1/2 for an electron. For an electron. In other words, the electron is a spin half particle. So, associated with this quantum number, there is a spin angular momentum denoted by capital S. This relationship is totally analogous to this relationship. So even if this is 0, S is never 0. Capital S. Capital S is under root 3 by 2 h bar. Because for an electron, small s is half. The quantum number is half. This 4th quantum number does not come out from the Schrödinger equation. It's a product of the mind of another great electrical engineer. His name was Dirac. So this property comes out from Dirac's equation. And Dirac's equation is based upon relativistic quantum mechanics. Schrödinger's equation does not deal with relativity, but if you put special relativity and quantum mechanics into a wedlock, they make the Dirac's equation. And the Dirac's equation tells us that there has to be a 4th quantum number, which is the spin quantum number. And just like the orbital quantum number, Sz is quantized. And is quantized according to ms h bar. And if s is half, ms takes the values half minus half. So Sz can be plus h bar over 2 or minus h bar over 2. ठीक है? Alright, so associated with the spin angular momentum, there is a magnetic moment. Just as if orbital angular momentum के साथ वाबस्ता है एक magnetic moment, spin के साथ भी एक magnetic moment वाबस्ता है. Therefore, the angular momentum is a combination of an orbital part. The magnetic moment is a combination of the orbital part and the spin part. Even if this is 0, this is non-zero. And that is what is happening in the Stern-Gerlach experiment. Now what is the relationship between mu s and s? We can write a similar relationship. This is a relationship between L and mu. So I can write a small l here to distinguish that this magnetic moment is indeed due to orbital motion. Okay? I can write mu s as an analogous relationship. Mu s equals E over 2m s. The only difference is that I have to put some constant of proportionality here. It's called G. Some constant of proportionality, which comes out from Dirac's equation. ठीक है, some constant of proportionality. Proportionality तो है, लेकिन एक constant डालना पड़ेगा. उसको G से denote कर देते हैं. This is not the acceleration due to gravity, of course. It's another constant, which is called the Landé's G factor. And for an electron, this G is very close to 2. G is almost equal to 2 for an electron spin. अभी तक बात समझ आ रही है ना? Everything is going, I'm going very slow but methodical, and so things should become very clear. So for an electron this is 2, which means that for an electron mu s is minus E over m s. Okay, I'm writing a subscript s to denote that this is the magnetic moment due to the spin part, and the z component will be minus E m s z. Now s z is m s h bar. What is ms? Plus minus half. So I will have plus minus E h bar 2m, right? But what is this? This is just the Bohr's magneton. So the z component of the magnetic moment of an electron, which has no orbital magnetic moment, is just plus minus the Bohr magneton. So the z component of s, of mu s, takes the value plus mu b or minus mu b, and this corresponds to ms equals minus half. This corresponds to ms equals plus half. Therefore in chemistry books, when you look at the periodic table and how the electrons go into different orbitals, one of these configurations is shown by an arrow pointing in the upward direction, and this is shown by an arrow pointing in the downward direction, because they have different z components. One has a z projection of the magnetic of the spin quantum number plus half, and the other has minus half. So they are drawn by two arrows, and we know that these are in fact tiny magnets. An electron is just like a tiny magnet which can point upward or downward. It can be parallel to the z field or it can be anti-parallel to the z field. Even if there is no orbital motion, there is no orbital angular momentum. So this spin is a fundamental property of the electron, and the electron is a spin half particle. So I have an electron, spin. Electron is a spin half particle. ms takes the values plus half minus half, and there is a value of the Landé G factor corresponding to the electron. It's 2. I can have a proton. Now the proton has spin as well. Proton की भी कोई spin है. And you cannot associate the spin with some orbital motion of the proton. But it is an intrinsic property of the proton that it possesses spin. And for a proton, you will have a similar relationship. Similar to this. So this, you can write a relationship for the proton spin as well. Proton. Just that you will have to use the G value for a proton. And you will have to use E over the 2 times the mass of the proton and the spin of the proton. So associated with the spin of the proton, there is a magnetic moment. So the proton has spin, and it's a spin half particle. Ms can be plus half, minus half, and the value of G is 5.6 for a proton. Consider a photon. Photon is a spin 1 particle. It has spin quantum number 1. So this property can be 1, 0, minus 1. You cannot define a G value for the photon. You can have a graviton. A graviton is a spin 2 particle. You can have a neutrino. Neutrino is a spin half particle. You can have a neutron. Neutron is a spin half particle. अब देखो एक बात important point. These particles that occur in nature, they have an intrinsic property called the spin. When we derived the orbital motion, we looked at the electron as a revolving charge. And associated with the charge, we found the current and we found the magnetic moment. But is the neutron a neutral particle or is it a charged particle? It's a neutral particle. But still, it has a spin. So the classical notion of a charge revolving causing a magnetic moment just breaks down. A neutron is also a spin. It has a spin. There are other particles, W particles, Z particles, they can have spin 0. The sodium nucleus has a spin equal to 1. For example, the ruthenium nucleus has a spin equals to 3 by 2. So different nuclei, different particles, they have different spins. And objects with spins 0, 1, 2, 3 and so on, they are given a special name and they are called bosons. And objects with half integral spins, half, 3 by 2, 5 by 2, 7 by 2, they are given a special name and they are called fermions. So spin is an intrinsic property of the electron. Last point I would like to highlight is the outcome of the Stern-Gerlach experiment. Now I give you half a minute or a minute to think, why does the beam of silver atoms split up into 2? सोचें और फिर हम continue करते हैं discussion. 5 more minutes to go. पहले मेरी बात का जवाब दो, फिर मैं आपकी बात का जवाब दूंगा. क्वेश्चन ये है कि स्टर्न-गर्लैक एक्सपेरिमेंट में बीम क्यों स्प्लिट होती है दो बीम्स के अंदर. Now we know that the electron has a spin. उसका फोर्सेस क्या एक्ट हो रही इन दोनों पे. आप बताओ.
क्योंकि म्यू एस होता है कौन सा दूर थी प्लस h फॉरवर्ड माइनस h फॉरवर्ड
फोर्सेस दोनों पे डिफरेंट एक्ट होंगी.
फोर्सेस देखिए एक तो जितना रिफ्लेक्शन की आगे में ऊपर जाएगा
एक अपवर्ड डायरेक्शन में फोर्स होगी, एक डाउनवर्ड डायरेक्शन में फोर्स होगी. फोर्स का क्या फॉर्मूला डिराइव किया है? So in the Stern-Gerlach experiment, the force that is acting in the z direction is given by mu z dB and the gradient of the field. Now mu z can take up the values plus minus mu b. So you can have a plus mu b dB by dz, or you can have a minus mu b dB by dz. So if you have a beam of electrons or beam of silver atoms, small l is 0, which means capital L is 0, which means mu L is 0, but small s is half because there is a valence electron which is unpaired. This is an unpaired valence electron. ये याद रहे बात. हाइड्रोजन एटम के लिए तो समझना आसान है क्योंकि इलेक्ट्रॉन ही एक है, लेकिन सोडियम में तो 11 इलेक्ट्रॉन है ना, सिल्वर में तो 26 इलेक्ट्रॉन है एटॉमिक नंबर उसका. ठीक है, तो देयर इज 1 इलेक्ट्रॉन इन द वैलेंस शेल व्हिच इज अनपेयर्ड. It's in an s orbital, which means small l is 0, but s is half, which means ms can be plus half or minus half, which means mu s can be plus mu b or minus mu b. So half of the electrons in half of the atoms, electrons will have a magnetic moment. Okay, now you apply a magnetic field. ये बात बहुत important है और subtle है. Subtle बात को सुनने के लिए खामोशी भी चाहिए. तो subtle बात ये है कि if you do not apply a magnetic field, in the absence of a magnetic field, you cannot tell what is the z-axis. But in order to make a measurement, in order to do something useful, you have to break the symmetry, you have to apply a z field. Now when you apply the z field, half of the atoms, almost half of the atoms will go in this state, that is their magnetic moments will point along the z direction, and for approximately half of the atoms, the magnetic moments will point in the opposite direction. And for these halves, that is for half of the atoms, the force will be acting in the upward direction, and for the other half, the force will be acting in the downward direction. So this beam will really split up. As it goes through the magnetic field, it splits up into two beams. But we also know that the field has to be non-uniform, otherwise this term will be 0. That is why we cannot have a uniform field and do the Stern-Gerlach experiment. And that is why you observe two distinct spots on the screen. तो हमें पता चल गया फील्ड होनी चाहिए टू ब्रेक द सिमेट्री. हमें ये भी पता चल गया द फील्ड हैज टू बी नॉन यूनिफॉर्म टू ब्रेक द सिमेट्री. Now the real power of quantum mechanics comes into play. This spin phenomenon cannot be described by any classical means. Spin, याद रखें मेरी बात, has nothing to do with motion about an axis. Spin is a misnomer, एक गलतुल आम लफ्ज़ है. गलतुल आम समझते हैं? गलतुल आम है, it's a misnomer. गलत नाम पड़ गया, लेकिन it has stuck because history determines what name sticks. Now I would like you to think about 2 or 3 things. Very interesting. You take this beam. Mu z is in the upward direction here and mu z is in the downward direction in this beam. You take this beam and subject it to another Stern-Gerlach experiment. You subject it to another Stern-Gerlach experiment in which the field is along the z direction. Will this beam split up again into two? It will not. It will not split up into two, because now we have selected an ensemble. We have selected only those atoms in which the magnetic moments are aligned in one particular direction. So this beam will not split up. So this path will be empty. That's why I am drawing it with a dotted line. ये path नहीं होगा. You will get just only one spot on the screen. If these measurements are done in quick succession, so that the magnetic moments do not realign and do not equilibrate again. ठीक है, ये एक जरूरी चीज है कि these experiments are done in quick succession. Now the question rises, I take this beam and now I perform a Stern-Gerlach experiment in which the inhomogeneous field is in the x direction. Now I have an inhomogeneous field in the x direction. Will this beam split up? Yes. Into how many? It will again split up into two beams, because you have only selected the z, the magnetic moments are aligned along the z direction. You have no knowledge of the x component of the magnetic moment, and there's an equally likelihood that one. Now this is your new quantization axis. Your new axis, your new symmetry breaking axis is perpendicular to the original axis, and these are independent measurements. So this beam will again split up into two distinct spots along the x direction. And again, now if you take this beam, the interesting thing happens now. If you take this beam and pass it through a z oriented Stern-Gerlach experiment, will you get two beams? Yes, again you will get two beams, because you have erased the memory of these spins. So now these are the counterintuitive concepts of quantum mechanics. Next, in the next lecture, we'll look at the technique of nuclear magnetic resonance.